Have you ever really stopped to think about how your computer thinks? I mean, this machine is incredibly complex, but it doesn't see pictures or words like we do. Nope, it speaks a completely different language. So, let's dive in and learn how to translate the secret language of computers.
Think about a simple number, something like 75. To you and me, it's just 75. Easy. But to the device you're watching this on right now, it's something else entirely. So how in the world does it translate our reality into its own? Well, to figure that out, we've got to start with the absolute basics.
And you know what? It all boils down to one core idea, a number system. Really, that's just a fancy way of saying it's a set of rules for writing down numbers. The funny thing is, we use one every single day without even giving it a second thought. And it turns out, understanding our system is the secret key to unlocking the computers.
All right, so let's start on some familiar ground, shall we? We all live and count in what's called a base 10 world. It feels totally natural, right? But believe it or not, there's a very specific structure to it that we can actually break down.
So the system we all learned way back in school is called the decimal system, or base 10. It's really built on 3 simple rules. First, it uses 10 digits, 0 all the way up to 9. Second, that number, 10, that's what we call the base, or radix. And third, and this part is absolutely crucial, where you put a digit in a number completely changes its value.
Yeah, this idea of positional value is everything. Each spot in a number represents a power of our base, which is 10. You've got the ones place, the tens place, the hundreds place. You get the idea. So a digit's value depends completely on which of those slots it's sitting in. Pretty simple, right? Okay, now let's take that exact same concept and see how it works inside a computer.
All right, time to jump into the digital world. Because inside your computer, the rules of the game change. A lot. The number of digits we have to play with shrinks from 10 all the way down to just 2.
When you get right down to it, a computer is basically just a giant collection of switches. Billions of tiny little electronic circuits that can be in one of 2 states. Either on, with electricity zipping through, or off, with nothing flowing at all. It's a completely black and white world, no shades of gray whatsoever.
So think about it. If our system is called base 10 because we have 10 digits, then a computer system which is built on just those 2 states, on and off, well, it's got to be base 2, right? And that's exactly what it is. We call it the binary system, and it only uses 2 digits, 0 and 1.
And here's the really important thing to get. Binary wasn't just some random choice. It's a direct reflection of how the hardware actually works. A 1 literally means an on state, an electrical signal is present. A 0 means an off state, no signal. Each one of these ones and zeros is called a bit, that's just short for binary digit, and it is the absolute fundamental building block of, well, everything digital.
Okay, but let's be real. Trying to read super long strings of ones and zeros would be a total nightmare for us humans. It's just clumsy. So naturally, programmers came up with a convenient shorthand to make their lives a whole lot easier. And that's where octal and hexadecimal come in. Octal is base 8, and hexadecimal is base 16. Just look at this example. The number 15 in our system becomes 1111 in binary. Kinda long, but in hexadecimal, it's just a single character, F. See how much cleaner that is? These systems are so popular because they convert really neatly back and forth with binary. They're basically a compressed, more human-friendly version of the computer's real language.
Okay, so we've met the different players here. Decimal, binary, octal, hex, but how do we actually, translate between them? How do we take our number, 75, and see it the way a computer does?
Well, the secret is a surprisingly simple trick. It's called the repeated division method. And honestly, the name pretty much says it all. You just keep dividing your original number by the base of the new system you want to convert to. It's that simple. Come on, let's try it out.
So let's circle back to our original number, 75, and let's turn it into binary. Remember, the new base is 2. So, first step, 75 divided by 2. That gives us 37 with a remainder of 1. Got it. Now we take that result, 37, and divide it by 2. We get 18 with another remainder of 1. And we just keep this going. We repeat the process over and over, dividing the new result by 2 and just keeping track of the remainder each time, until we can't divide anymore.
Okay, now here is the most important part of this whole trick, so listen up. You do not read the remainders from top to bottom. You have to read them backwards. You assemble them in reverse order, starting with the very last one you found and working your way back to the first.
And the coolest part? This method works for any base. It's universal. Let's prove it. Let's convert the decimal number 305 into octal, which is base 8. We do the exact same thing. Just keep dividing by our new base, which is 8 this time. We collect all our remainders, a 1, a 6, and a 4, and then, reading them backwards, we get our answer. So, 305 in our world is 461 in the octal world. How cool is that?
And that right there brings us all the way back to our original question. The number 75 to a computer is actually 1010111. It's not one thing. It's a sequence of 7 tiny switches being flipped. On, off, on, on. That's it. That's the language.
Just think about that for a second. Every photo you take, every song you listen to, every single complex app on your phone, it is all built on that ridiculously simple foundation of just 2 digits. It's kind of mind-blowing to think about the insane complexity that grows from such a simple seed. It really makes you wonder, doesn't it? What's the next fundamental language we're all going to have to learn to understand the machines of the future?